work, and energy. Introduction. Living beings have to perform several basic activities to survive. We call such activities life processes. The energy for these processes comes from food. We need energy for other activities like playing, singing, reading, writing, thinking, jumping, cycling, and running. Activities that are strenuous require more energy. Scientific conception of work. To understand the way we view work and define work from the point of view of science, let us consider some situations. A girl pulls a trolley bag and it moves through a distance. The girl has exerted a force on the trolley bag and it is displaced. Therefore, work is done. Lift a book through a height. To do this, you must apply a force. The book rises up. There is a force applied on the book and the book has moved. Hence, work is done. By constant force. Consider a situation in which the force and the displacement are in the same direction. A baby pulling a toy car parallel to the ground, as shown in the figure. The baby has exerted a force in the direction of displacement of the car. In this situation, the work done will be equal to the product of the force and displacement. In such situations, the work done by the force is taken as positive. Let the object stop after a displacement s. In such a situation, the work done by the force F is taken as negative and denoted by the minus sign. The work done by the force is F into minus S the whole or minus F into S the whole. Energy. Let us consider the following examples. When a fast-moving cricket ball hits a stationary wicket, the wicket is thrown away. We have also observed children winding a toy such as a toy car, and when the toy is placed on the floor, it starts moving. An object having a capability to do work is said to possess energy. The object which does the work loses energy, and the object on which the work is done gains energy. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is joule, J. 1 J is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule, kJ, is used. 1 kJ equals 1000 J. Forms of energy. The various forms include mechanical energy, that is, potential energy plus kinetic energy, electrical energy, and light energy. Nature of energy. In our day-to-day life, we come across several forms of energy. Mechanical energy that pumps water out of a well. Heat energy that boils the milk we drink. Electrical energy that lights the bulb. Chemical energy in batteries used in torches. And solar energy that plants need to grow. Kinetic energy. Set up the apparatus as shown. Place a wooden block of known mass in front of the trolley at a convenient fixed distance. Place a known mass on the pan so that the trolley starts moving. The trolley moves forward and hits the wooden block. Fix a stop on the table in such a manner that the trolley stops after hitting the block. The block gets displaced. Note down the displacement of the block. This means work is done on the block by the trolley as the block has gained energy. Repeat this activity by increasing the mass on the pan. In this activity, the moving trolley does work and hence it possesses energy. Potential energy and kinetic energy. Suppose you take a ball to the top of a tower. It will possess only potential energy. The heavier the ball or the greater the height of the tower, the greater will be the potential energy of the ball. If you release the ball, it will fall to the ground due to gravity. As it falls, its kinetic energy by virtue of its motion increases, but its potential energy decreases. When it hits the ground, it will have maximum kinetic energy and no potential energy at all. At any time from the release of the ball to the touchdown, the sum of the kinetic energy plus potential energy is constant. In other words, The gain in Ke as the ball is released is equal to the loss in potential energy. The law of conservation of energy states that energy can neither be created nor destroyed, but it can merely be transformed from one form to the other. Kinetic energy equation. Consider an object of mass m moving with a uniform velocity u. Let it now be displaced through a distance s when a constant force F acts on it in the direction of its displacement. The work done, W, is Fs. The work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let A be the acceleration produced. The relation connecting the initial velocity u and the final velocity v of an object moving with a uniform acceleration a and the displacement s is v squared minus u squared is equal to 2as. This gives s is equal to v squared minus u squared divided by 2a. F is equal to ma. We can write the work done by the force F as W is equal to ma into v squared minus u squared by 2a the whole, or W is equal to 1 by 2 m into v squared minus u squared the whole. If the object is starting from its stationary position, that is, u is equal to 0, then W is equal to 1 by 2 mv squared. It is clear that the work done is equal to the change in the kinetic energy of an object. If u is equal to 0, the work done will be 1 by 2 mv squared. Thus, the kinetic energy possessed by an object of mass m and moving with a uniform velocity v is Ek is equal to 1 by 2 mv squared. Potential energy of an object at a height. Consider an object of mass m. Let it be raised through a height h from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of the object mg. The object gains energy equal to the work done on it. Let the work done on the object against gravity be W. That is, work done W is equal to force into displacement is equal to mg into h is equal to mgh. Since work done on the object is equal to mgh, an energy equal to mgh units is gained by the object. This is the potential energy EP of the object. EP is equal to mgh. It is useful to note that the work done by gravity depends on the difference in vertical heights of the initial and the final positions of the object and not on the path along which the object is moved. The figure shows a case where a block is raised from position A to B by taking two different paths. Let the height AB is equal to h. In both the situations, the work done on the object is mgh. Example: find the energy possessed by an object of mass 10 kg when it is at a height of 6 m above the ground, given g is equal to 9.8 m s to the power of minus 2. Solution: mass of the object m is equal to 10 kg. Displacement height h is equal to 6m and acceleration due to gravity g is equal to 9.8 ms to the power of minus 2. From equation, potential energy is equal to mgh is equal to 10 kg into 9.8 ms to the power of minus 2 into 6m is equal to 588 joules. The potential energy is 588 joules. An object of mass 12 kg is at a certain height above the ground. If the potential energy of the object is 480 joules, find the height at which the object is with respect to the ground, given g is equal to 10 ms to the power of minus 2. Solution: mass of the object m is equal to 12 kg. Potential energy EP is equal to 480 joules. EP is equal to mgh. 480 joules is equal to 12 kgs into 10 ms to the power of minus 2 into h. H is equal to 480 joule by 120 kg ms to the power of minus 2 is equal to 4m. The object is at the height of 4m. Law of conservation of energy. Whenever energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation remains the same. Potential energy plus kinetic energy is equal to constant, or mgh plus 1 by 2 mv squared is equal to constant. Rate of doing work. Consider two children, say A and B. Let us say they weigh the same. Both start climbing up a rope separately. Both reach a height of 8m. Let us say A takes 15 seconds while B takes 20 seconds to accomplish the task. What is the work done by each? The work done is the same. However, A has taken less time than B to do the work. Who has done more work in a given time, say 1 second? Power is equal to work divided by time, or P is equal to W by T. Units of power. Units of power are shown below. Example: a boy of mass 50 kg runs up a staircase of 45 steps in 9 seconds. If the height of each step is 15 centimeters, find his power. Take G is equal to 10 ms to the power of minus 2. Solution: weight of the boy, mg is equal to 50 kgs into 10 ms to the power of minus 2 is equal to 500 n. Height of the staircase, h is equal to 45 into 15 divided by 100 m is equal to 6.75 meters. Time taken to climb, t is equal to 9 seconds. From equation, power P is equal to work done divided by time taken is equal to 500 n into 6.75 m divided by 9 seconds is equal to 375 W. Power is 375 watts.